Hello everyone, my name is Prakul Balaji and I'm a third year EPH student. As part of the Fundamentals of AI and ML course, this is my project. The topic of the project is ML based classification and summarization of chess playing styles. So, what is the aim of the project? The aim of this project is basically to develop a framework to identify chess player personalities using behavioral features and to apply clustering algorithms to the features and determine the various playing styles. So this is done by giving a set of chess games of a particular player. So what I've done is I've taken a particular player and taken 16 of his games and calculated a few aggregate metrics based on that. And using these metrics, I've done the clustering. I've applied the clustering algorithms. So what is the motivation behind this project? So as we know, chess games offer measurable behavior data. So based on the moves of chess players, we can identify their behavior. And when it comes to chess, there are millions of games available in the database today, in the online databases. And using this, we can understand the psychology of players by evaluating their moves. So this project can basically help in profiling a player, and this uh, process can generally be used in preparing against players. So basically, in high-level chess tournaments, people generally prepare for their opponents based on the set of moves they've played in previous games. So this can add the emotional features as well of the players uh, during game preparation, and this can also be used by coaches to understand their players in a better way. So the dataset for this project, I've used Lichess's monthly online games, and this is their website where they dump monthly online games. I have chosen a random month here. I've chosen 2015 December as the dataset for this project. So from this dataset, I've filtered out 16 games of each player, and I've considered around 275 different players for this. And I have calculated a few aggregate metrics, which include stuff like ACPL, which is the centipon loss. I'll get back to it later. And the win percentage and overall trends of material imbalances and position evaluations. And to avoid noise, I've considered only longer format games, which are classical and rapid games. This is because in shorter formats, the accuracy of players and many such things, they differ a lot. So to reduce the noise, I've removed such shorter format games. So the metrics I've used for the players is first and foremost one is the average centipon loss. Centipon is basically okay. So in chess, there are certain values given to pieces. The smallest one being that for a pawn, which is 1 point. So a centipon is basically 1/100th of the value of a pawn. So when I say centipon loss, it means how much the evaluation of a position differs after a person makes a move. So, for example, before a move, the evaluation was 0.4 centipons, and after a move, it becomes 0.5 centipons. So the loss is -1 basically. So basically, there's any uh, increase in centipon, which is actually worse for the player. So it's basically 0.1 the loss here. The next metric is the material imbalance. Material imbalance is basically the difference in material between the two players. A plus, for example, a +2 material imbalance will be uh, 2 points in favor of white, and if the material imbalance is -2, it would be 2 points in favor of black. The next metric is win percentage, and I've calculated it for separately for against higher rated players and lower rated players as well. And the next three metrics are more of emotional metrics. These uh, try to evaluate the emotional aspect of players and quantify them. The first one is fighting capability, which is the number of moves the game goes on for after a player reaches a losing position. That's basically what fighting capability means. The next one is the comeback index. As the name suggests, it's the ratio of games in which the player wins the game after reaching losing position. And the collapse index is basically the vice versa, the ratio of games in which the player lost after reaching a winning position. So the workflow of the project, the first step is to acquire the dataset from glitches, as I just showed, and the file was of .pgn.zst file. It's basically a compressed file consisting of several PGNs. PGN is the uh, actual file, a single file that consists the details of the game, and so the second was to decompress these the ZST file into separate PGNs. So, and the third step is to update these PGNs as data into CSV file. And the next step is to clean this data to remove unwanted games. As I said, for example, I removed the games that were of shorter formats. So the fifth point, it's basically until the fourth point, the data is in such a way that there are games in the games are in random order. So each row corresponds to one game. So going from the fourth step to the fifth step, what I've done is I've grouped those games for a particular player. So I'll I'll explain this in detail when I'm showing the code. The sixth point is integrating the Stockfish engine. Stockfish is a widely used chess engine which uses something called the UCI. UCI is the Universal Chess Interface. So this is basically the language of chess, and it uses terms such as PGN. As I said, PGN file is part of the UCI, and it uses a few headers. Headers is basically the place where information is stored, and yeah. The next step is feature engineering, and after that, once again, I've cleaned the data to avoid any discrepancies in the data. After which, I've applied clustering. Here, I've applied two clustering algorithms. One is the k-means algorithm, and the next one is Gaussian mixture models. I'll explain that in detail. And after which, the next step is to assign the cluster. So after clustering, since we don't have ready-made data to determine which cluster represents which personality, I've adopted a certain method to assign the clusters to the its particular playing style. And the last step is to predict the cluster given a new player's data. So clustering. So here I have used two clustering algorithms. One is k-means and the other one is Gaussian mixture model. K-means is basically the first step to trying to segregate the data points into clusters, into distinct clusters. And after which, the reason why I've used Gaussian mixture model is because when it comes to personalities, it's not that a player possesses only one kind of personality. At times, the player can possess a mixture of two or more personalities. So, what GMM basically does is it assigns a probability that a data point belongs to a cluster. So, it could be such that if there are personalities, personality 1, 2, and 3, it could be that person can belong to, has a probability of 75% of personality 1, 10% of personality 2, and 15% of personality 3. So this is the reason why I used GMO. So I'll be moving on to the code. So this is the code for the first step. This is, I have saved it as decompress IPYNB. So I've imported the required libraries here, and then and this is for decompressing this RST file, which has numerous PGNs. So I'm separating the PGNs first, since each PGN has one game. and I'm parsing those BGMs, and from the BGMs I get these headers. These are the information of each game. So I'm getting information such as events, and site is basically the link, the online link to the game. The player who played white, black, the result, white, yellow. Yellow is basically the rating of the player, and the kind of opening they played, which is a very important information. It just, although I haven't used it in my prediction, it's a very important feature of the game. The date and time at which it was played, and termination. Termination is the kind of way manner in which the game ended. It could be either through a time forfeit, or it could be through a normal, such as checkmate or resignation. So this is, yeah. From here, I've parsed about 200,000 games, 2 lakh games basically, and I've saved it to a file named parsedgames.csv. So this is the first step, and the next step is to clean the data. Sorry. So this is where I've used so this is where I've removed the games which have shorter formats. As you can see, I've tried to, not tried, I've actually let me just search for it. Oh, sorry, it's not here. What I've done is in the decompressed file, there was this, yeah, so there was this event. In the beginning, it was uh, the time format was not given as classical blitz or rapid. What was given as it was given to be a tournament game, a classical rapid tournament, classical sorry, classical tournament, and solo tournament, like tournament games which are not part of the tournament. So from that event column, I have tried to I've classified the time format and whether it was part of a tournament or not. So this is what I've done here, and basically these are the cleaning. There are no missing values as you can see, and the total unique players were around 26,000. And this is the game format distribution. Uh, yeah, so this is the distribution of players with more than 10 games. Uh, because less than 10 games is not very good for calculating aggregate measures. So I have only considered games that are more than 10. Consider players who have played more than 10 games. Sorry. So as you can see, as the number of games increases, the number of players tends to spike, since many players don't play a huge number of games. And this is the distribution of the game termination types. Yeah. So this is the part of the code where I have removed the games which are bullet and blitz. I only considered rapid and classical games here, and the total number of games I've uh, uploaded is 90,000, around 90,000. And this is has been saved in a separate file, classicalgames.csv. And as you can see, it's been saved over, yeah, over here. So yeah, I think I closed the file. Maybe. Yeah. So I've removed the games which are less than 10 moves, since for games less than 10 moves, it's not generally considered to be good, since there are many outliers in it, because a player tends to blunder earlier in the game, which kind of creates sorry, which kind of creates inaccuracy in the data. And I've also removed the games in which the rating difference between players is more than 250, because generally higher, very very high rated players tend to dominate the game. So the accuracy of the low rated players can get affected. So that might create a noise in the data, and that's why I remove such games. And I've also removed games which have less than 20 moves and forfeit because it's very rare in nature, so I wanted to delete it. So I've cleaned the data and I've so this is where I've um, changed the structure of the data. So what I've done is I've uh, basically in the beginning the data was structured in such a way that there was a particular game in which the person who played white was given, the person who played black was given, and the rest of the details were given. So what I've done now is since I want the games of one particular player, what I've done is I've removed the columns for white and black. I've uh, I've taken a new column with just one player's name, and in the next column, which is the color he's played, I've mentioned whether the player has played white or black. So, so from a game-centric data, I've shifted it to a player-centric data, and I've exported it to a new CSV file, feature extract of CSV. So the next step is basically feature extraction. So for this, I first evaluated the metrics which don't require the chess engine stockfish, and these are simple metrics such as the mean number of moves, the number of moves, and then for the aggregate statistics, I've taken the mean number of moves, the standard deviation of moves, and uh, and then I've calculated the win percentage as well, and the win percentage against high rated players, and the win percentage against low rated players as well. And I'm exporting it to a new CSV file, training data.csv. So the next step is to evaluate the metrics using Stockfish. So first I downloaded Stockfish, the chess engine from this website, the Stockfish's own website. And as you can see, I've saved it in a folder Stockfish, and this is the executable file. Just a second. Yeah. So this is the .exe file, and and that's the path I've given here. And just to mention, this is the data set. I've saved the data set of here. I forgot to mention it earlier. So, so what I'm doing here is uh, in the feature.extract, uh, in the feature extract.csv file, uh, the details of the game were given, and one of the columns were listing out the moves. So what I've done here is I've used Stockfish to evaluate the position at each move. And as you can see, I've added new columns. One is eval list, and the other one is material difference list. So basically, what it does is it creates a list of evaluations at each move. So if the moves column had about let's say 30 entries corresponding to 15 moves, the evaluation list will give you 30 entries evaluating the position at each of the 30 moves and the material difference at each of the 30 moves. So I've uploaded to the feature extract.csv, and I've uploaded about 4400 games. I actually had 10,000 games, but due, since Stockfish is a very CPU heavy engine, it requires a huge amount of computational power to to process it. So since uh, due to limited computational power, I had to stop at 4,400 games. But yeah, so using better computational power, we can increase the number of games, and we can increase the number of data points. Exactly. And yeah, as I said, I have printed out the moves, eval list, and material difference columns. So So this 32 is corresponding to this D4 move after the move is played, and D5, 24 corresponds to D5. So I have given the corresponding evaluation list and the material difference list. So the next step is to compute the metrics, the average centipond loss and other such metrics using Stockfish, and I have uploaded to training data.csv file, which is over, yeah, which is over here. So in this whole code is to evaluate the aggregate metrics, and yeah, this is where I uploaded the emotional metrics, as is the fighting capability, the comeback index, and the collapse index. For this, I've used something called T loss. T loss is the point at which a player reaches a losing position for the first time and for two consecutive moves. So if the game is for around, let's say, 30 moves, and the player first reaches a losing position at around 20 moves, the value for T loss will be 20. So this is required to evaluate the fighting capability. For example, since the fighting capability in this example will be 10 moves, because after the T loss at 20, the game went on for 10 more moves. So the fighting capability, the number of moves for fighting capability will be 10. And based on that, I've calculated a particular index. So the index will be 0.33 in this case, since it's the number of moves after T loss divided by the total number of moves. So this will be 0.33 in this case. So using T loss, I've computed the emotional metrics, and I've saved it to training data. And okay, I've filtered only the players for whom the games were evaluated. As I said, it wasn't possible to evaluate all the games. I was able to evaluate only about 4,400 games. So I have filtered those players only, and I've saved it in a new file. So the next process, so after feature extraction, there might still be discrepancies in the data. As you can see here, there are certain rows null values in these, for example. So the main point behind this Jupyter file is to clean the data after feature extraction, and I've printed the correlation heat map over here. As you can see, there's a high high correlation between in-loss games and in-loss games for comeback. In-loss games is, it's not the number of games the person lost, it's actually the number of games in which the person reached a losing position at some point. And in-win games is the exact opposite. And as you can see, there's a high variance between mean ACPL and mean game ACPL variance. Mean ACPL is the average centipond loss. Average centipond loss is taken over a game, and the mean ACPL is taken over 16 games. And mean game ACPL variance is almost the same, but there's a slight difference. It's the variance in a centipond loss within a particular game, and then I've taken the mean for that. So, but as you can see, there's a high correlation between these two. So I have dropped one of those columns. I have dropped the mean game ACPL variance, and I have dropped the username column as well, since we are about to apply the clustering algorithm, and we need only numerical values for that. So that's why I dropped the column. And yeah, so this is the file, and I have uploaded it to training data clean. So all the feature extraction and cleaning are done. The next step is to apply the clustering algorithms, and that's what I've done here. This is clustering final dot the Jupyter file. So I have taken different values of k and tried to figure out what the best value of k would be. Since we can assign the value of k for k means clustering algorithm. And I have printed out the Silhouette score here. Generally, for determining the best value of k, we need to take the Silhouette score, which is very high. But the problem here is it's not actually a problem. Um, the higher value of Silhouette scores is for k equal to 2 or and 3. But since we are trying to see different playing styles, 2 and 3 are not very good values over here. So I've taken the next best value, which is 5. And as you can see, I've applied PCA here. PCA is principal component analysis, which reduces the dimensionality. I've reduced it to 2 here for to show it in a 2D map. And this is the clustering. This is how the clustering looks after applying PCA. As you can see, their clusters are almost very well distinct, except for probably this cluster, which is not very distinct, but still you can see that there is a difference between these both clusters. I also tried to plot the clusters for considering different values of k. As you can see, k equal to 2 and 3 are very well distinct, but as I said, the problem is we are trying to analyze the different personalities. So 2 and 3, the number is very less. So k equal to 5 could be a very good score if we consider more number of data points. Here we have only 275 players. So generally for clustering we need at least more than 1000 points, 1000 data points. But as I said, due to Stockfish's limited, not limited, very high computational power is required for this. So at this level, it's not possible to get more than 1000 data points. So that's why I could get only 275 here. So this is where I've applied the Gaussian mixture model, the GMM, and as you can see, this is the table. Um this is the table assigning the data points, uh, probabilities of data points to different clusters. As let me just take an example. If you consider this data point, for example, cluster 1's probability is 0.2, and cluster 4's probability is 0.79 in this case, and the probabilities for the remaining clusters are very less. So as you can see, it assigns probabilities to different clusters, and since the probability of it being in cluster 4 is very high, it finally has taken cluster 4. And okay, so we have done with applying the algorithms, clustering algorithms, k-means and GMF. So the next step is to assign the cluster to each playing style. So for that, what I've done is I've normalized the features for each cluster, and I've tried to print what how much each feature dominates in each cluster. As you can see here, uh, for example, let's consider cluster 2 here. Sorry, cluster 1. As you can see, the mean ACPL is very less. I'm not sure whether I mentioned the lower the value of ACPL, the better it is, because since it's a measure of loss in centipoints, so the lower the loss, the more accurate the player plays. So as you can see, the mean ACPL and standard ACPL, standard deviation of ACPL, the values are very low for cluster 1, and the mean number of moves is also very dominating. So this could mean that the player generally plays long and accurate games. So it's more of a very technical player. And I've I've mentioned the labels and summary over here. I mentioned it in the PPT as well. I'll show it in some. So for cluster 1, the label is enduring strategists and solid fighters. So These are very technical and accurate players who tend to play more accurate moves, and the game goes on for more number of moves generally. And I've classified the remaining clusters in similarly. And what I've done here is I've taken a new CSV file. Just a second. Yeah. So new players.csv. This contains 10 rows with 16 numerical features. So it consists of the data of 10 new players whose data was not already there in the training data set. This is part of the prediction data set. And uh, so this code basically tries to predict which cluster each pair can belong to, and it gives a confidence measure as well. As you can see here, the first data point has been assigned to cluster 0, and confidence is 1 for this particular data point. And for the second data point, for example, it's cluster 4, and it's been assigned a probability of 0.7. So that's all for the code. I'll be getting back to the PPT. Yeah. So yeah, as I showed in the code, these were the results I obtained for the clustering algorithms. This is the interpretation for each cluster. Um, I've assigned personality labels to each cluster and also given the reason for that. For example, as we saw for cluster one, they had very high mean moves and standard deviation of moves, very low mean ACPL and standard ACPL, and high fighting capability. I guess I missed this in the code, but they also it's over here. High fighting capability. Yeah, the fighting capability. Okay, it's not very high, but it's uh, a very good measure. So even if the person reaches a losing position, they are able to fight. So that's why the name is given. There's there could be a second name given to it as well. You can name them solid fighters. But basically, the online summary remains the same. They're long, technically sound games and persistent fighters who win by steady play. So similarly, for cluster zero, I've named it solid technicians. For cluster two, it's highly successful imbalancers. Imbalancers here basically means they tend to play with material imbalances generally and not equal materials. So that's why the imbalancer's name is here. And short game brawlers, these are the players who play very fast and aggressive games and tend to make many inaccuracies. So basically, they're high risk and high volatile players. And the cluster 4 is overextended fighters. They tend to have high fighting capability and standard deviation of moves, and yeah, and they have very low win rate. So even after reaching a losing position, the game tends to go on for many moves, but at the end, their win rate is very less. So they try to fight for very long, but at the same time, they are not able to uh, convert the games. So there were but certain challenges I faced during this project. One was understanding the format of the dataset. Since it was of the form .pg and .zst, and and the decompressing the files was a bit time consuming and a bit difficult to understand. The next major challenge is I've said multiple times. It's the time complexity. As I said, Stockfish is a very CPU heavy chess engine. So due to computational limits, I was able to create only 275 data points. And using better computational power, we can increase the number of data points, and this could result in better clustering. And the next major challenge was interpreting the clusters. As I said, there is no particular labeling available uh, for assigning the clusters to a particular playing style. So for this, I had to look at which features dominated in each cluster, and I provided the labels of clusters based on that. Overcoming a few challenges to reduce noise, I considered only classical games. As I said, shorter formats induces noise in the data, and generally emotional behaviors are very tough to quantify. It's generally a very qualitative feature, but over here, what I've done is I've tried to introduce new features such as the fighting capability, the compact index, and the collapse index to sort of quantify the emotional behaviors that can be understood from a chess player's moves. So I've also removed games which had a low number of moves and very high number of moves. Low number of moves is because uh, the accuracy could be very less in such games, and in games with higher number of moves, generally the problem is when a position is has reached a dead end. No player can win from that position. It's basically a draw. And if the players continue making random moves, the chess engine will still show it to be of 100% accuracy. So to avoid any such noise, I remove such games as well. So the conclusion. Hmm. So the data points were successfully clustered into different playing styles, and these clusters were summarized as well. But however, due to computational limits, the number of data points had to be reduced. So this can be increased by using higher computational power. So increasing number of data points and features can result in better clustering and classifying, as I said. So this project provides a method to quantify behavioral aspects of a player through his or her chess moves. So possible future work for, for this project. So we can include more data points and more features as well. I've introduced about 16 features for this project. So this can be increased. We can, for example, include timestamps as well. After 2017, we just started introducing timestamps, uh, showing the time left on the clock. So based on this, we can also try to quantify emotional aspects based on how much time is left on the clock. So and this project can also be extended to include offline games. Since I've introduced only online games for this project, we can in- include offline games as well. And these are the references for this project. Thank you. Hope you enjoyed the presentation.